All right. The assignment that's related to StormCAD and some sizing of ponds is due on Monday. We're going to do the empirical estimates for required storm pond sizing, the Ashton method and Apton-Grigg. These two methods are kind of less sophisticated than solving for the required size of the pond using Excel. And so the Excel is kind of the hard way, and then if you ever need just a quick and dirty, very fast estimate and don't have Excel available, then either of these methods can kind of get you in the ballpark. Any questions related to the announcements? Okay, one other thing I wanted to mention is you probably have already seen the email announcements that the DOH is going to be having like an open house talking about the summer internships that they have available. And that's this coming Monday at 5 p.m. And even if you're not interested in working for the DOH, I think they're providing food, so it could be a free meal. But if you have nothing else going for the summer, then you could definitely do worse than an internship with the Division of Highways. I think some of our students have had kind of boring internships, some have had really great internships, and even if you don't end up working at the DOH after graduation, just kind of seeing the inside view of how things operate there could be useful. Let's say, for instance, if you end up at a consulting firm.
The signs in the lobbies say 5:30. It's an inconsistency.
That does seem to be one. Yeah, the slide that they emailed us said 5. So I guess if you're there early, maybe you'll get the food while it's still hot. All right. So this is what we're going to start off with. Just to reiterate what you did in the example that was worked with the recorded lecture, let's consider an office park that has a lot of roof area and paved area, but somehow by maybe using pervious pavement or putting in vegetative filter strips and so on, they've used a variety of best management practices to bring the composite C value for the site down to 0.70 for this 5-acre site. 5 acres isn't the pond area, it's the area of the development that we're going to be sizing a pond for. The pipe that goes out of the pond has a discharge coefficient, and I wrote the ideal version of the orifice equation here on the board earlier, but in reality, when you account for losses having to do with the water approaching the pipe and turbulence and so on, it's customary to include a pipe coefficient, a C factor, and 0.6 is kind of in a typical ballpark for that. And so the flow rate Q would be the cross-sectional area of the pipe multiplied by C multiplied by the square root of 2GH. Maximum allowed pond depth for this design, we're going to assume 6 feet is the limit. You just don't want to have too much depth for not only safety reasons, but also because of water quality concerns. If you have a really deep pond, the water at the bottom of the pond doesn't get enough oxygen. And there can be anaerobic conditions down below there, and essentially sludge and worms and bugs that are associated with anaerobic conditions can occur, and it can give off unpleasant gases like hydrogen sulfide. So there's a variety of reasons why we wouldn't want a pond depth to be too great. The side slopes assumption, of course, in the pictures we've looked at before of stormwater ponds, let me see if I can, I have one specifically in mind, a picture from earlier. It was a dual-use pond that was both, here we go. All right, so this is a stormwater pond, the one at the lower right. And you'll notice that the side slopes aren't vertical. It's kind of like a trapezoid in all 3 directions, all 4 directions. And so when we assume that it's a rectangular shape or that the side slopes are vertical, it makes it a lot easier to calculate because the surface area doesn't change as the depth is going up. So the reality is if you do have tapered side slopes that extend outward, then the water depth isn't going to be as large as you otherwise would expect, because when you make the assumption of vertical side slopes, you're saying that there's this tray of water. And if the pond is actually having side slopes like this, then you're neglecting the capacity to contain water on those side edges. Now, that volume isn't generally going to be huge in comparison to the rest of the pond. You know, if you're talking about a maximum of 6 feet of depth, then that would be 6 feet on either side of the trapezoid, where some of these ponds will be 200 and 300 feet in each dimension. That ends up being not negligible, but pretty small. All right, so if you have Excel open, I'm going to give you a handout that summarizes these same constraints that we've been looking at on the screen. Here's the hydrograph. This is the water that's coming into the pond. You know, if you analyze the rainfall behavior, you can generate a hydrograph like this. And so assume that that's already been done, and the municipality that this office park is being built in has both a local ordinance and a state ordinance that apply. And so we want to make sure that our pond satisfies both criteria. The first criteria, and we're going to analyze them separately. The first criteria says that the water coming out of the pond is limited to 0.1 CFS for every developed acre. So if our area is 5 acres, what does that mean our outflow limit is? 0.5 CFS. What's the peak flow coming in from the hydrograph that's on the screen? This is the flow that's coming in. 7.9 is coming in, and the most that can go out is 0.5 CFS. And so what we have to do is design a pond that the storm is doing this, where we have time on the horizontal axis and flow rate on the vertical axis. This is the storm is causing water to run off of our developed area at a really high flow rate. And if we just dump that straight into the creek, there's going to be flooding, there's going to be scour. And so what we need to do is design a pond that dumps it out a lot more slowly. And it's not that the overall volume is going to be decreased, it's just we're delaying the timing of it. Okay, so criteria A would limit our outflow to 0.5 CFS. Criteria B would be representative of the statewide ordinance, which says you have to retain the first inch of precipitation. So what that means is, over this 5-acre site, you should have enough volume in your pond to retain all of the water that runs off of a 5-acre site during a 1-inch storm. So Q equals CIA, you would use the C value, you'd use the area of 5 acres, and you're assuming 1 inch of precipitation. So what volume of water is that, and can our pond hold it, is the question. All right, so I'm going to give you the handout that just summarizes all of this. We're going to use basically the same column headings as was illustrated in the previous example. Let me write those on the board in case you don't have them handy. Okay, so in your spreadsheet solution, I think the first column should be time. The second column should be inflow and CFS. The third column should be volume in during time increment. The fourth column should be accumulated volume, and this is going to be in cubic feet. Since we are in traditional units, time will be hours, inflow CFS, volume in during time increment is going to be cubic feet. Okay. The fifth column, column E, is going to be the pond water level depth in feet. Column F would be our depth to orifice centroid. In other words, that's the H parameter, and that's also in feet. Column G is going to be outflow from pond in CFS. And column H would be the volume out during increment. So we're talking about how many cubic feet are going in during a 1 hour time period and how many cubic feet are going out during a time period. Now, the outflow during a time increment is going to be 0 during the first hour. The outflow, of course, is going to be based on the depth. And so you're going to have to set up the orifice equation as Q equals area times V, which is the square root of 2GH. And we're also including the coefficient of discharge for the pipe. Not the runoff coefficient, but the C sub D of 0.60. All right. So I'm going to pause the recording and give you some time to set that up. And I think that this will probably be pretty good practice for not only the homework, but also upcoming quiz opportunities. So this is a design, and we don't know what the size of the pond is yet. So you'll notice that on the spreadsheet that I'm putting together here on the screen, for pond width and pond length, I don't have anything yet. And I'm not sure how big this pond is going to need to be. Let's say, is it going to be 500 feet by 500 feet? Maybe. Let's just use that as a starting point, and if that's the starting point, then the cross-sectional area would be the length times the width. I also don't know what pipe diameter is required, because both of these things are going to affect what the flow rate out is. The length and the width is going to depend on, is going to influence how deep the water gets, and then the pipe diameter affects the flow rate out, and both of those things are interrelated. So as a starting point for the pipe diameter, let's say, what if the pipe diameter is 2 feet? So if the pipe diameter is 2 feet, then I can calculate the cross-sectional area of the pipe from that. All right, so let me just make sure that everybody's got this part before we go any further. Let me make it a little bit bigger. All right, so if during the first hour, well, at time 0 there's no flow in, and so then the volume in is going to be 0. There's no water in the pond yet. Right at the beginning of the storm, there's no water in the pond. So the depth of the water is 0. There's no depth to the centroid. The outflow is 0. Everything's 0 at the beginning. And then if you have 1 hour of an inflow at 1.8 cubic feet per second, then that's the flow rate times the time. And there's 3,600 seconds in an hour. And so 1.8 CFS for a 1 hour period means that there's 6,480 cubic feet that flow in during that hour. I guess I'm going to just center everything because I prefer the way it looks. Oh, jeez. There we go. Okay. So we can drag that formula down through each of the time increments, and that's how much is coming in during each 1 hour period. So each row on the spreadsheet represents a 1 hour period. And so the accumulated volume is saying what's the difference between the inflow and the outflow. And so we only had inflow. If you look at the outflow, there was no outflow during the previous hour, and so the accumulated volume is simply going to be how much came in this hour for the accumulated volume. And so if there's that much volume in a pond that has this area, we can find the depth by being volume divided by the area. Anchor the reference to that so that as I drag the formula down, it's always looking in this spot for the pond area. And anytime I change the dimensions, it's going to dynamically update the area of the pond.
On the time hour 2, I did not get the 12,960. I got 25,920.
Did you type in 3.6 CFS as the flow rate?
Yeah.
During the hour 2?
Yep, 3.6.
So you multiplied 3.6 by 3,600, and what did you get?
No, I did not. I only multiplied by 2. Oh, I times it by the hour as well.
Hour 2 is just, it's that's the number of the hour. There's still only 3,600 seconds in that hour.
All right.
So each row represents a 1 hour period.
Okay.
All right. Now, what you'll notice is the water depth is only 0.03 feet for how big this pond area is. And so if the depth of the centroid is, let's see, this part, the height of the pipe center line above the bottom of the pond. So this is essentially half of the pipe diameter, so I'm going to do equals the pipe diameter divided by 2. This factor is what I'm going to use to calculate H from the water depth. But the problem that we have right now is that the water is so low that the orifice equation isn't going to describe the flow out. In other words, let me draw a sketch of it here on the whiteboard. Right now, with the design that we've got, here's the bottom of the pond, here's the pipe out, and the water depth is only this high. And so it's not going to be the orifice equation. The opening has to be fully submerged for us to be able to calculate the outflow by the orifice equation. So we'd need to put in a different equation like the Weir equation or something, but this can be a pretty good indication that our pond is oversized. If the depth is that low, it probably means 500 by 500 is too big. So let's swing the other direction. Let's say, well, what if it's 100 by 100? All right. So it's way less shallow now, and it's likely that our pipe diameter is also too big. So let's try, what about a pipe diameter of 1? Okay, so now H is going to be the water depth minus this parameter. And so if the water depth is 0.65, so what we're saying now is the water depth from the bottom, 0.65 is this distance, and then if we're using right now a 1 foot diameter pipe, and half of that is 0.5, so then the distance from the water surface down to the centroid, I guess we should do, so if the water depth is 1, then we should have half left over. So the pipe isn't yet fully submerged. So this shouldn't be positive until we have it fully submerged. Let me just think for a second. I'm like a deer in the headlights at the moment. So if it was a half, 0.25, 0.65. Yeah, it's set up right, but it's still not, since it's not fully submerged, then the orifice equation, it's not going to really give us an accurate result until the pipe is fully submerged. But let's just go with it for now and see where it takes us. All right, so if this is the depth of the centroid, then, okay, yeah, it's fine. Then the outflow is going to be the cross-sectional area of the pipe, anchor that reference, times the discharge coefficient, anchor that reference, times the square root of 2 times G, 32.2.
Oh, you're supposed to ask us which one.
Yeah, times H, which is F12. Okay, I can't click on that since I centered it. The formula is kind of in the way, so I wouldn't have been able to click on the cell location, but I can type it in. Okay. So we're using the orifice equation even though it's not quite fully submerged, but if that's the outflow, then the volume out during the time increment is going to be that outflow rate times 3,600. So this is now the volume that's out. Alright, so now this is the one other tricky spot, is accumulated volume. So what we want to know is how much is going to be in the pond at the end of the second hour. And what we have to do is use the outflow from the previous hour in order to estimate that. And so the accumulated volume is going to be the previous hour's volume plus the new stuff that comes in minus the volume that went out during the previous hour. And this is kind of akin to numerical integration, where we'd have better resolution if we were doing this in 15-minute time increments or 5-minute time increments. You know, it sometimes seems a little bit strange that you're using the volume that flowed out during the previous hour to find the volume at the end of this hour, but there's an interdependency between the flow rates and the water level, and so that's why we have to rely on a previous hour's outflow to find out the accumulated volume during this hour. Alright, and now the pond water level, we can drag that formula down. And so if there's this much water in a 100 by 100 pond, now we have the depth. For that depth,
I just heard like 3 errors in my area.
I didn't anchor the reference to this last one. Okay. So if the water depth is 1.42, then the H is 0.92. And so it's subtracting out half the height of the pipe. So that's correct. And now the outflow is going to be based on the area of the pipe, the C sub D, and square root of 2GH.
So CD times the area, and then times the
Square root of 2GH, where the G that you're using is 32.2 because we're in traditional units. Alright, so then the volume out is going to be 3,600 seconds of this outflow rate. Alright. Now at this point, since we have the accumulated volume set up correctly to include both the previous hour, the flow rate in during this hour, and the previous hour's outflow, we can drag all of these cells down at the same time by highlighting them. And so let's just drag the next one and see if it's behaving the way it ought to. So what we see is that the pond water level is getting deeper, and anytime the pond is getting deeper, that means there's more coming in than there is going out. So what we have right now is, I just guessed, what if it's 100 by 100, and what if we have this pipe diameter of 1 foot? So this is what the pond is doing when those are the design parameters. So I drag this down, and let's analyze the pond all the way through. Don't be thrown off if it says this. It's just you're dividing by 0 and there's no more flow rate in. So let's see what's happening. So here's the inflow, and what we said is that we can't have more than 0.5 CFS coming out, and the depth of the pond should be never more than 6. So we're okay as far as the pond depth. We're not close to that upper limit of 6. But what about the outflow? We're way too high. Okay, so if the outflow is too high, how do we make sure that there's less water going out of the pond? What's the outflow based on? if we look at the formula, it's based on the discharge coefficient, which we don't have direct control over, based on the pipe area, which we can control, and then the depth of the pond, which we have indirect or secondary control over. So what we can do is we can make the pipe diameter smaller. Right now there's too much flow going out by a lot. We're only allowed 0.5 CFS, and right now there's like 6.3 CFS, 6.4. So it's kind of taking the edge off a little bit. You know, we have 7.9 coming in and 6.4 going out. So it's a little bit better than if there was no pond. And also it delays it, and that's advantageous to delay the peak. But the pond isn't doing yet what it needs to be doing. So what you should do is change the width and the length, and you know, maybe it's just easier if you assume it's going to be a square, so you set the length equal to the width, and then you can just say 101 feet long, 102 feet long. Play around with the dimensions and the pipe diameter until you're very close to the pond depth being 6 feet. So get as close as you can to 6 feet, because what that means is you're using less pond area. And you know, this is a 5-acre site where they want to put in buildings and parking, and they're less interested in having a huge stormwater detention pond. So you want to maximize your allowed depth to minimize the cross-sectional area of the pond. So you want to make the width and length progressively larger until, and make the diameter progressively smaller until you've optimized to have just the maximum outflow is, so let me write this here, that our limit for the outflow is 0.5 CFS. So that's kind of the target that we're looking for. And the thing that'll make it even easier for us to find it is if here we use the max formula. You've probably used it before. What you can do is you can select a range and you just say, tell me what is the max within this range. And right now our max value is 6.4. So if our limit is 0.5 and the max is 6.4, we're too high. We need to make that pipe size smaller until the limit doesn't exceed the max. And then the same thing we could look at for the depth. Like our limit, the allowable limit, and what's the max. Let me drag this up.
You said the numbers between on the outflow pond, correct?
Pardon me?
On the max equation, what did you select? What?
The outflow, because our design criteria is that we're limited to 0.5 CFS. So it's the outflow. And then our depth limit, so just to clarify, this first limit, what we're looking at, has units of CFS. That's our outflow limit. And our current maximum that we see during the storm event. And then the allowable limit of the depth of the pond and the maximum that we currently see in our design. And so the current maximum that we see in our design is 3.3, and we're permitted to increase the depth all the way up to 6. And so as you make the pond outflow pipe smaller, it's going to make the depth go up. So for instance, what if we use a pipe diameter of 0.7 feet? So right now our maximum is 6.4. What if I say 0.75? So that's an 8-inch pipe, right? No, 3/4. 9-inch pipe. 3/4 of a foot. Anyways, 0.75 feet. Now our flow rate is closer to what it should have been. So we were at 6.4 when the diameter was 1 foot. What about 0.75? Now the max is getting closer to the limit. Also, the pond just got a lot deeper as well. We are very near this 6-foot limit. So that may mean that we need to simultaneously change the dimensions and the pipe diameter. So I'll give you some time to optimize the design. To really see what's happening over the long term, you need to have more than just the 12 rows, the inflow data. You know, the pond is going to be draining for a long time after it stops raining. So that's why I have it going down through 36 hours, is I want to see how long does it take for the pond to get to a certain depth. If you have the width 159 feet and the diameter of the pipe 23 feet, then the outflow gets pretty close but doesn't go over 0.5. So, you know, if we look at more digits of accuracy there, we're getting 0.485. So I guess maybe I could make the diameter a little bit bigger, maybe 0.35. No, now it's over. So to the nearest tenth of a foot, it's 0.23 is the pipe diameter we should go with, because that's the one that now is seeing that the outflow doesn't go too high. And why did I choose this width and length of 159? It's because now the maximum depth is very close to the limit of 6 feet. So this is kind of the ideal combination. This is the ideal optimum design, where we want to limit the outflow to no more than 0.5 CFS, and the water depth in the pond can only be as much as 6 feet. So the two parameters that we were adjusting is the width, which also tells us the length, and then the diameter. All right. We need to pause for just a moment so that I can show you how the AASHTO and the apt and grig methods work. They both are simplifications of what's actually happening during a storm. And a storm isn't necessarily linear. The runoff from a watershed isn't going to go linearly up to its peak and then taper linearly down. But that's what both of these methods assume. And in both cases, what you're doing is you're calculating the volume of storage that's needed, because that's the difference between what comes in and what goes out. And so the inflow hydrograph is the one that has the higher peak and that peaks earlier. The outflow hydrograph is the one that has the lower peak and the peak is later. So if you know an allowable discharge flow rate, and if you know the peak flow rate that's going to come in, what the AASHTO method says is that you can assume a triangular hydrograph for both of those, and the base time you assume is twice the time it takes for the water to go to its peak. And so then the storage volume is just half of the base time times the difference between the peak flow rate and the outflow allowable flow rate. So it's kind of the area above the curve, above the outflow curve, but below the inflow curve. And the apt and grig method uses a similar approach, but what they do is they're saying, let's not have a triangular outflow hydrograph. Let's have a constant flow rate out, because that's more realistic in the case of the flow conditions from a pond. And just as an illustration of how these two methods compare, let me show you an example where if we wanted to compare the AASHTO method and the apt and grig method, and we knew the flow rate that can come out, 450 liters per second, is going to come into the pond off of the development, and we can only discharge 80 liters per second. And so, you know, there's the peak that's coming into the pond, the flow rate that's allowed out of the pond. Both of those are defined. And then also this is saying an inflow discharge duration of 90 minutes. So that discharge duration is defining how long it's going to occur, how long the storm event is going to occur, the time to peak. So I mean, these methods are essentially just plugging the numbers into the equation and just running it through your calculator. But the thing that's interesting is that even though those methods are relatively different, they can yield the same result. And So I'll send you the solution so that you can see how AASHTO and Apton Grigg kind of compare and the volumes that are required. If you didn't get all the way through this spreadsheet, you know, the steps are recorded in the video, but you'll get a chance to practice it one more time in the homework assignment that's due Monday. I'll be in my office this afternoon if you want to stop by and ask me any questions on the homework. I'd be glad to help you out. So I will see you on Monday.